Okay, so I guess we'll wait a couple more minutes for people to show up. But thank you for joining us for this interesting exercise in this interesting times. Please bear with me if anything funny goes on and any technical difficulty comes up. But hopefully you can hear me now. So if you can please confirm on the live chat whether I can get through to you, that'd be really awesome. And it'd be also nice to see who's around, because I can't see who you are until you type something in the chat. So throughout the entire lecture, feel free to interrupt me as you usually do. There is, however, a 30-second delay between what I do over here and what you see over there. So when you ask a question I don't answer right away, I'm not ignoring you. It just takes a bit of time for the signal to get through to you. So good to see everybody. Yeah, let's get started. This is 11, so so today we're doing Ampere's law, and then we'll also quickly do paramagnetism, diamagnetism, and ferromagnetism at the end. And then also we'll briefly talk about the midterm at the very end. So hopefully it'll take, the last time took about an hour. It'll be around here for this section too as well. So thank you for your attention. All right, Ampere's law. So last week we did a bunch of integration to find magnetic field around different size and shape wires, different points around those things, and it can get quite tedious and somewhat difficult with all the direction happening. So similar to how we got tired of integrating with electric field and we came up with Gauss's law, can we do a similar thing here with magnetic field that looks at the entire magnetic field line kind of diagram? And in fact we do, and that's how we end up with Ampere's law. But first, let's think about what Gauss's law was trying to tell us. Right, Gauss's law was saying that, okay, we noticed that for a point charge you can get all kinds of electric field, looking way back, right? And the expression for these electric field is kq over 4 pi r square. And there's this idea, this term here, which looks like the surface area of a sphere. And then we also notice that if we draw a little sphere, we can kind of relate the number of lines going out to infer that there's some positive charge inside the volume enclosed, right? So that's how we came up with Gauss's law that relates what happens at the surface, the amount of line that goes through the surface. So this is through a closed surface with some statement about whatever happens inside the volume enclosed. And through various high symmetry cases, we can make use of that to find the electric field a little bit easier than to do the full integration bit. And it also allows us to further on flip it around and do a derivative form instead, and it goes on and on from there. So can we apply the same thing for magnetic field? Well, the catch with magnetic field is magnetic field always gets generated in these loops. So if I were to draw a Gaussian surface here, I see that I have 3 lines coming in, and I have 3 lines coming out. If I go here, I have a bunch of lines coming in, right? And I have the same number of lines going out. And this works for not just for the loop of current, but for a solenoid, right? Same thing here, a bunch of ins, a bunch of outs. And it actually applies to permanent magnets as well, right? Because we actually tend to draw the lines, magnetic field lines, within the material of the permanent magnet as well. And this being a dipole, you have, again, in equals out. So in all these cases, even for a straight wire, of course for a straight wire, because these are all circles, right? Everything goes in, everything comes out. Even if I include part of the wire, we're still going to get the same thing. So this leads us to this thing called the Gauss's law for magnetic field, where it relates the net flux of the magnetic field through a Gaussian surface, and that's always equal to 0. This is in fact another basic statement of the fact that we never ever observe what we call a magnetic monopole. We never see just a north pole sitting in space, similar to how we would see negative charges, a negative point charge sitting in space, where all these magnetic field terminates. Sorry, all these electric field terminates. So for a magnetic field, that doesn't exist. You have no magnetic monopole. You don't just have a north pole sitting there emanating magnetic field. It always comes in pairs, and therefore your magnetic field always draw these loops. So Gauss's law is pretty mundane. Like, while it's a fundamental law of the universe that explains the basic fabric of how our universe works, it's not immediately useful for us to make use of this to find the magnetic field at any given point. So instead, people modify their view a little bit. So we can't use Gauss's law exactly. And the clue to using Gauss's law and not being able to use Gauss's law is that with Coulomb's law, right, we have this thing that looks like the surface area of a sphere. So that clues us in to be using, surface area, enclosing volume, etc., etc. You could argue that with the Biot-Savart law, we also have the r square dependence and 4 pi r square under here, but the direction doesn't work quite as well as with Coulomb's law. So instead, we're going to make use of this other form. So if you have a straight wire, then the magnetic field swirls around it, right? And the size of this magnetic field, or I guess we'll practice our right-hand rule. The size of this magnetic field is equal to mu naught times I over 2 pi r, r being the distance from the wire to wherever this point is. And that is a hint for us that we're looking at the circumference, or the length of the loop around the circle, which then hints that we might be able to use the circumference of a circle, right, to make a loop, to relate it to the area enclosed in a loop. And in fact, that is what we do, what Gauss's law is basically saying. If we track the magnetic field on all points on this loop, we can say something about what is the current going through it. So the form of Ampere's law ends up being, so not dA, because we're not talking about flux, it's dL. And we still have this thing to remind us we're using a closed loop. and it's related to the current enclosed, related by this constant mu naught. And that's where the definition of mu naught kind of comes from Ampere's law. So Biot-Savart law uses this same constant, so we have to divide by the 4 pi. So what does this all mean? Well, if we take a current, we know that it makes magnetic, and if we're interested in the magnetic field at a particular point, right, that is r away, we know that in here, the magnetic field at all these points kind of make a circle around the wire. If we then track the component of the magnetic field around a circle in this loop, and that's where this dl comes in, right? There's these little mini step as we go through the different chunks of my loop. If we track the component of magnetic field along that direction, and we add those all up, it would correspond to and be related to how much current is inside that area. Now this thing is not flux. We call it a loop integral. We don't usually define a special symbol for that. But while we do this, we have to define the sign a little more carefully to be consistent, right? Because by the right-hand rule for current and magnetic field generated around that current, we kind of know the direction relationship already, so we have to be consistent with that. What we mean by that is, in order for the current to be positive in this case, right? To be out of the page, if we call out of the page positive, that must mean that whatever this line integral is, this loop integral, this BDL term, has to evaluate to positive. And that would be true if we choose to integrate in the counterclockwise direction in this case, where your DL and your B goes in the same direction. But if we take the exact same case, and we choose to integrate in the clockwise direction instead, then at these points, your B would be in the opposite direction. So your dot product will evaluate to negative instead. So to make that consistent, we must say that the current, in this case, coming out of the page has to be negative instead of positive. So here we're demonstrating how the integration direction that we choose is intimately related also to the side of the current that we call positive. Which then brings us to yet another right-hand rule, which is this. It's in one of these thumbs up one because it's, and again, relating something that goes in a circle with something that goes straight. In this case, if your finger curls along your integration direction, then your thumb points to the direction of positive current. Now, notice here, very important here, that the integration direction and the direction we call positive in terms of current has nothing directly to do with the actual direction of the magnetic field or the current itself. It's just that if the current happens to be in the direction of our thumb, then we call that a positive current. If the current happens to be in the direction opposite to our thumb, then we call it a negative current, right? It's just our way of defining positive, negative. So for the counterclockwise case in green, we use the right-hand rule and we see that the thumb points out of the page, and so we'll call the current in that of that wire coming out of the page that we've drawn, that's a positive current. But if we were to integrate the other way, right, then our thumb points into the page, but the current is still coming out of the page, so we call that a negative current in that case, which corresponds to the fact that the dot product evaluates to negative, so you get negatives on both sides, and Ampere's law is still consistent. Now, one more thing about the direction and Ampere's law is it's not necessary for the current of that kind of goes through the area to go through it perpendicularly, or even taking just the perpendicular component. The beauty of Ampere's law is that it works as long as you're going from one side to the other. So if we flip that loop edge on, right, you would see something like this, right? That's the loop. And let's say the loop comes out on top and in the bottom, then using our right hand rule, right, you should get, my finger should point towards me on top and into the page on the bottom. So I'm defining positive current to be, in this case, to the right. So any current that kind of goes to the right we call positive I, right? But it can be at an angle, right? That's positive I, right? And anything that goes through the other way, we'll call it a negative current. That's a negative current. Those are all negative currents. So that's how we incorporate the direction with Ampere's law as well. And of course, at this point, you'll get a number of questions that will deal, that's pretty basic, right? That will deal directly just asking, what is the total loop integral given a certain situation? And those are the easy ones, right? Just like how in Gauss's law we had those when we just asked about the total flux, so we only care about the charge enclosed. So in this case, if we ask about the entirety of the loop integral and not just the magnetic field at a specific point, we only care about the current enclosed, right? We can work out the current enclosed without doing this messy integral business. The only added complication is you have to be careful what you call positive current and what you call negative current based on the integration direction that you choose or you're given. The other class of questions would be to actually find out the magnetic field at a specific point using Ampere's law, and that only works for a few cases with very high symmetry so that the loop integral turns out nice, much like Gauss's law. The first case we'll look at is the infinitely long wire, right? This is the case of cylindrical symmetry. And the basic problem is you have a current, right? Let's say it comes out of the page, and we want the magnetic field of a point that is r away from the wire. So at this point, what is the B? Well, Ampere's law basically assumes that we already have some sense of what the direction of the magnetic field is, and we know that from the right-hand rule, so we know it swirls around this way. Not really a circle, but whoop, right? So then at this point, locally, it's pointing up. So we know the direction already. It's just that we're trying to find the magnitude now. So then, to use Ampere's law, we have to draw not a Gaussian surface, but an Amperian loop. We draw an Amperian loop that includes this point, so that we can say something about that. But we draw in such a way that we have the symmetry, so that every single point would have consistent direction with the loop, and also this magnitude hopefully remains the same. And the one to draw would be a circle of radius r. So at all these points, you know that the magnetic field runs in the same direction as your loop, every single point. So we specifically choose that B is equal to dl at all points, and that they have the same magnetic field, magnitude. So that when we go ahead and do Ampere's law, again, we can do these two sides kind of separately. So this side of the loop integral, we already said that B is parallel to dl, so that's just the magnitude of B times the magnitude of L, and then that can come out of the integral because it's the same everywhere in terms of magnitude. So we end up with the magnitude of B is equal to the loop integral of dl, magnitude. And the magnitude of dl would be the size of the circle, circumference around the circle, 2 pi little r. For my current, because I have chosen to take the integral counterclockwise, I use my right hand and tell me that, oh, positive current is out of the page. In this case, my current is in fact out of the page, so this is positive I. And we end up with divided by 2 pi r. Right? The same result as we've done with all the hard work of using Biot-Savart law, integrating it along a wire, and then making that wire infinitely long. So at least now we can see that Ampere's law is consistent with what we've done before, but that doesn't tell us anything new, right? However, Ampere's law does simplify things in certain circumstances and allows us to give us a little more insight. In this case, the one extra step we can take is consider not a point outside the wire, but if we're looking at a point inside the wire. So now we draw the wire a little bit bigger, right? You can imagine there's basically current through this wire everywhere, and they're all going out, but I'm not going to draw that many circles. But we're interested in the magnetic field, some points inside the wire. The wire itself has a radius big R, let's say. So we want the B here. Again, we expect the magnetic field using the right-hand rule to be in the upwards direction at that point, perpendicular to this radius. So we will once again draw a Gaussian, an Amperian loop that includes a point I'm interested in that obeys a symmetry. In this case, a circular loop. And we're again going to integrate counterclockwise, just so my current can remain positive. And so we do the same thing. And again, the same kind of symmetry applies. So these are parallel at all points, and then B is the same. So we end up doing the same thing on the left-hand side, giving us B times 2 pi little r is the loop integral. But for your I enclosed, right, we're only taking part of the current, right? Because we're not including the entire wire. We're only including just part of that wire. And as we went through when we discussed current not long ago, that in wires, the current is distributed uniformly throughout the wire. It's not like it's stronger in the middle and weaker on the edges or the other way around. It's going to be uniform. So if we're taking a portion of the total current, right? The portion is the total area divided by, and then the enclosed area. And sometimes people group these things together and call that current density, right? Much like how we had charge density and whatnot. So current density is defined to be the current divided by the cross-sectional area of the wire. In the end, it really just lets us say we're taking a portion of the current because we're only enclosing a portion of that area. So putting that all together, you have I total divided by the total area, which is pi big R square. You multiply by the area that is actually enclosed, pi little r squared, right? Be careful which r to use where. Things cancel out, and we end up with the final result, which is for a point inside the wire, you don't have a 1 over r dependence like you have outside the wire. You have a r dependence, a linear dependence. And that's because as you get further out, yes, your loop is getting longer, but the area you're enclosing is also getting larger by r squared. So if you were to do this with integration, it would be a lot more difficult because then you have to cut up the wire into a bunch of little wires and then find out all those contributions added up. So Ampere's law is good for some things. Just like Gauss's law, Ampere's law is really good at the things it's good at. The other case I want to go over with you, which is quite important, is the infinitely long solenoid. Right? We talked about last time that we did a bunch of hard work, right? We started with a current element, then we integrate that into a loop, and then we made a bunch of loops into a solenoid, and then we set the length of solenoid to infinity to get us our final result. And even at that result is only saying that anywhere along this middle line, right, we expect the magnetic field to be the same along this middle line inside the solenoid. So I already said last time this particular shape is very important because it gives us a uniform magnetic field. Not only does it give us a straight line field, it's also uniform. So I'll now use Ampere's law to prove to you that not only is the magnetic field the same all the way along, but also across the cross section as well. And here's the setup. So we slice this open right down the middle. That's what we'll see, right? In this case, all the current is coming out on the bottom and in on top. And the other requirement is we're making this infinitely long. So while in this diagram, right, the magnetic field can come out of the solenoid and loop back around. Imagine if this was really, really long, then these things just keep going forever and they don't get to loop back around and escape. So as a result, everywhere inside this infinitely solenoid, the magnetic field is created and straight, and they can't escape out the end. So outside, there's no magnetic field. Now, if you're interested in finding if the direction of the magnetic field goes left or right, what my recommendation is, I look at one single piece of wire and do my right-hand rule on that. So if I look at this piece of wire, then it's coming out of the page. I use my right hand, it tells me it swirls this way. So then inside my solenoid, it goes that way. So I know, therefore, everything adds up, and they all add up to give you. If you pick a point up here, you find that it swirls this way, clockwise. It also gives you that way. Everything's consistent, just the way the geometry works. So if you ever want to find out the current of the magnetic field inside a solenoid, just look at one single wire and see what they're doing, what that particular piece of wire is doing. Anyway, so now that we established the outside has no magnetic field, we can then draw a Amperian loop of this shape, this rectangular shape. And then apply Ampere's law. Now when I do this integral, I'm cutting out the different segments, and each part I kind of do separately. Let's do the easy part first. So these parts, because your B is equal to 0, therefore your BDL integrated around here would also be 0. So we can just ignore those parts. That's the easy part. Next, if we look at these two chunks, right? Yes, the B is not 0 here, but here your magnetic field is perpendicular to your DL, right? DL in this case would go that way. So therefore, when you do the dot product with two things that are perpendicular to each other, that's going to be, the dot product becomes 0. So outside the solenoid, because the solenoid is infinitely long, right? For a regular solenoid, that's not infinitely long. The only reason why there's fields out here is because they kind of loop around out the end. Whereas if you imagine this thing become infinitely long, then they never get to escape and loop back. So that's one way to justify that. You can also kind of go through and do the integral and see how everything cancels out as well. Is that enough, David? So then whatever's left is just this last piece here, where your B and your DL goes in the same direction. And because of symmetry, your magnitude is expected to be the same as well. So your loop integral, once again, turns out to be very, very simple. And that's just the length of this line, which is L. So then, now we have the I enclosed. So how many wires are we enclosing? Right, it's not just the one wire because there's a whole bunch of different wires here. So it's the current through each loop of the solenoid multiplied by the number that's enclosed. Now remember that this L here has nothing to do with the actual length of the solenoid, right? It's just a length of the loop that we choose to take. But we can then say, based on the length of this, we're enclosing so many number of loops. So we're going to change this and call this the loop density once again, right? Loop density. And this gets us the exact same result as we had through doing all that hard work last week. So the number of loops within a particular length, that's the loop density. Again, consistent with what we got through integration, but the added insights here is that this whole derivation would be the same if we made the loop this big, this big, this big. So anywhere along here, right, all these different points would give you the same result. So all along the area, all along and across the area, we expect the magnetic field to have the exact same magnitude. So now we really have a magnetic field that is straight, a magnetic field that is the same along the axis, and also a field that is uniform across the area. So really we're getting this uniform magnetic field, both magnitude and direction. And so Ampere's law allows us to prove that much easier for the infinitely long case than if we were to have to do it with some kind of integration, because if it's off axis, the math gets pretty ugly. Another case I'd like to go with you then is the toroid shape. So a toroid shape is basically like if you took a solenoid and you took the two ends and you join them together, right? And a way to visualize it, actually I'll look up some images. Right? Oh, wait, not that. So you can look at like a slinky, right? Loop back around itself like that. So you take a slinky and you join the two ends up and make it like a circle like that. That's a toroid, right? Down here you can kind of see, if you cut it sideways, you'll see that each link is also a circle in this case. But that's not necessarily, that doesn't have to be the case, right? Each link could be a square or a triangle or star shape or whatever shape, right? But as you loop it around, right, whatever cross section this is, the outside will still look like a circle. Does that sort of make sense? And in any case, we're going to analyze it the exact same way, whatever shape it is. We're going to cut this right across the middle like that. Right across the middle like that. And what we end up with as a result is a cross section that looks like this. Yes, that is a result that we do get. The magnetic field inside a infinitely long solenoid is in fact independent of the area of the solenoid itself. You can think of it in a way that, yes, there's more area to fill, but there's more wire around it to make the magnetic field as well. So it kind of balances out. Okay, so back to this toroid thing. If we are then interested in the magnetic field of a particular point, what this cross-section is trying to show us is the current kind of comes out here and into there, like that, out of a wire, into a wire, kind of like that. And then if we're interested in the magnetic field at a particular point, what we know is that it acts more or less like a solenoid, so it will be parallel to, I guess, the tangent of the circle. And to find out the direction once again, yes, in all cases, if you change the current, you'll get a different magnetic field, including the solenoid case. back to this. So if we want the direction of the magnetic field inside the toroid, then again we look at one specific wire, in this case wire coming out, then it's going to loop like that. Then we know that the magnetic field will run around the toroid in that direction. It's all consistent. So if you try this one, you have to point your thumb into the page, and again inside the toroid, consistent all the way around. See? Okay. So if we were to find the magnetic field here, we would draw an Amperian loop that's also circular, just to obey the symmetry, right? And in this case, again, we have your magnetic field magnitude the same, and that your B and DL is parallel. So again, we do all the exact same thing. So Ampere's law once again. Gives you B times 2 pi R here, R being the size of my Amperian loop, or the distance of my point of interest away from the center. And then the I enclosed here is the current through each wire, but look at how many wires it's inside. Well, in this case, I use my right-hand rule because I'm integrating counterclockwise. I know all the outgoing current is known as positive. Then I see that all these currents are positive, and I'm counting all the loops, right? So this is the total loop, and not the loop density, right? I have all the loops inside my Amperian loop, which gives us the result that's not so complicated. Of that. Which incidentally is fairly similar to my solenoid case, because you have the total number of loops on top, big N, divided by the total length sort of thing, right? This 2 pi R. So one thing to keep in mind when dealing with a toroid is that the field is, unlike the solenoid, it's not uniform. Right? It depends as a 1 over R dependence, which is sort of saying that, on the inside edge, the loops are tighter together, right? Your loop density is higher, so therefore you get a stronger magnetic field. When you're on the outside edge, they're a little more spread out, so then you get the magnetic field just a little bit weaker on the outside. But on top of that, we can also ask ourselves, what is the magnetic field outside the toroid? Say here, or here, or here, right? And there we draw different Gaussian Amperian loops. So if we want this point, low r, we draw an Amperian loop that goes around this way, right? And because I enclose is 0 in this case, and with the symmetry, that leads us to say that by Ampere's law, that's equal to 0. Therefore, your magnetic field must be 0. And similarly, for the case outside, right, if you want this case, we draw this Amperian loop, and we find that the I enclose, you're enclosing all of the wire that are going outwards, and we call those positive, right, by the right-hand rule, yet again, plus all the current that are going into the page, and then we must call those negative. So n times I minus n times I give us 0 yet again. So then out there, your B is equal to 0. So for a toroid, all the magnetic field is trapped inside of the toroid within here, and there's no quote-unquote leakage of magnetic field outside the toroid, and that has certain good uses, especially in terms of circuit, because you don't want any stray magnetic field that affects other parts of your circuit. So it does not create. So that's kind of why a toroid is a preferred shape for some application, even though the magnetic field inside is not exactly uniform. So let me see that question. So yes, closer to the inside. That's right. So on this side of the toroid, the magnetic field is slightly stronger than on that side of the toroid. Again, because of the 1/r dependence. But once you're outside the toroid in here, then you have no magnetic field. So that's kind of all the cases for Ampere's law that kind of I'd go through with you, and you kind of expect to know. That's kind of it. There are some limitations of Ampere's law. The first one being just symmetry, right? It's very similar to Gauss's law, right? If we can't make this ugly integral play nice, then we can't find the magnetic field at a specific point. Right? That doesn't make Ampere's law not true, right? Just like Gauss's law is true in general, but we can't use it to find our magnetic field at a specific point without introducing too many other variables. However, unlike Gauss's law, there's an additional requirement that the current has to be steady, meaning not changing in time. Because when it does change in time, there's a completely separate physical phenomenon that comes into play, and we'll cover that hopefully by the end of the term. Nonetheless, for this week and for definitely the midterm, and whenever we apply Ampere's law, you can assume that the current is in fact steady, so you don't have to worry too much about that. Yes, for the toroid, the R is always measured from the center out because it is the size of the Amperian loop that we're using. So let's go back here, right? So the R is from the center out because it's the size of this circle right here. Okay, so if you give me 10 more minutes or so, I'd like to just go through this one last thing, dealing with magnetism in matter, right? When we talked about capacitance, we talked about how given the presence of some solid material that's not simply vacuum, right? We have to modify our permittivity of free space into this kappa times the permittivity, right? This dielectric constant. Because the dielectric partially polarized and partially canceled out some electric field. So we have to modify that. Similar things happen with your magnetic field, right? You have to change the permeability of free space from a vacuum to kappa mu naught as well. However, most material can be classified into one of three categories, and we're going to talk about those really briefly right now. The model that kind of happens is, you can think of, like that video was talking about, I show you, each individual atom more or less acts like a little tiny magnet, right? With a tiny little bit of magnetic dipole moment. And these things, if it's exposed to some external magnetic field, will tend to align with the magnetic field, and therefore, in fact, add to the magnetic field. So unlike the electric case where you're partially canceling out, any solid matter within sitting in a magnetic field tend to add a little bit of magnetic field by this alignment. However, for most material, this effect is not too strong. And by the strength of what happens here, we classify material into under three different names. First, we have the paramagnetic case. The paramagnetic case is where each atom themselves, or each molecule, I guess, have some magnetic dipole moment. Not a lot, some, but they only align weakly. And it's hard for them to shift. Maybe it's because of due to thermal agitation. If they're locked in a crystal lattice, then they don't get to move around so much. So the alignment is weak, but it still adds a little bit. And so that your kappa B is in fact greater than 1 because you're still adding. But we're usually talking about on the order of 1.00001. The effect is very small for most of these things. And then as soon as the magnetic field goes away, they tend to get randomly jostled back around, and then you lose that magnetism. Then there's another case called diamagnetic, and in those cases, the diamagnetic atoms have no moments at all, right? No dipole moment at all. So therefore, no matter what happens, there's no alignment, and then you might think, oh, it acts just like a vacuum then. But unfortunately, there is another small effect that comes up. In the absence of the alignment, this other effect called Faraday's law comes into play and becomes significant because nothing is bigger than it. Actually makes it a little weaker. And Faraday's law I think we'll cover next week, so you don't have to wait long. So therefore, kappa magnetic field is less than 1, but again, the effect is really not strong, so we're talking about 0.99991 or something like that. The interesting case is the ferromagnetic material, where the atoms have really strong magnetic dipole moment that aligns very, very strongly. In fact, many of these material, the alignment is so strong that once you expose this material to an external magnetic field to cause that alignment, the magnetic field created by the resulting alignment can maintain itself, and that's where we get the idea of a permanent magnet. It can sustain itself. And just to give you an idea, right? Iron is a very well-known ferromagnetic material, and the kappa for it, it's on the order of 5,500, right? Compared to 1, right? This is huge. Which also means that if you were to use a coil to generate magnetic field, right? You would normally do B is equal to mu naught Ni. Well, you now modify that to kappa. In this case, I use K, mu naught Ni. So we're basically, if you insert a iron core inside your solenoid, you're getting 5,500 times the magnetic field for the same current. Right? So it's not very efficient to create magnetic field just with a coil wire sitting in air. If you stick an iron core through it, you're going to get a much, much bigger magnetic field. And so for most electromagnets, you'll see that there is actually a core inside like that. And not only do these materials work to enhance or, I guess, amplify the magnetic field effect, it also has this effect of channeling the magnetic field, because it's much easier for the magnetic field to go in the material than otherwise. So last time I showed you the application of a hard drive, and this is how you can make use of these material to channel, right? The coil was up here in the red, generating the magnetic field. Oops. That kind of goes that way, right? But then these magnetic field gets channeled within the iron instead of going out into the air, because the material much more prefers it. And so you can make applications like these kind of right heads where you generate the magnetic field so that it channels, and then as it jumps through the air gap, that's the only point, and you can very precisely have only that one point exposed. Or if you make it a funnier shape, you can make it go up and down much stronger here, and then spreads them back out on the other side, so on and so forth. Is the core a shell? No, usually we have a solid core just because we can. There's no limitation to make it not solid. In fact, we want the whole thing to be filled with iron if we can. So that's kind of the cutoff for the material you're responsible for this midterm. So let's talk about the midterm really briefly then. So the midterm, as I've sent out by email, will be still take place on Wednesday, March 25th. I think that's right. Anyway, next Wednesday, whenever that is. And the email will be sent out to you by 10:30 a.m. with a PDF enclosed with the midterm in it. And if you haven't received anything by 10:40, please email me. So I don't know, something might have gone wrong, but please let me know. It's technically open book. You have access to all the material you wish, but I still really, really, really recommend you make yourself 1 or 2 reference sheets just for the sake of, I guess, speed, I guess. You know, to have everything in front of you, you don't have to like look it up, you know, open up that slow e-text book, find that particular equation, right? So get that all ready, then you should have no problem. I would expect you to submit the midterm on Brightspace sometime with the due date 4 hours after I sent it out. So in your case, it will be 4:30 p.m. The length and the style is expected to be pretty much exactly the same as the previous midterm. So similar to midterm 1, similar to the old midterms I posted. They are not expected to be way harder, no. There will still be 5 multiple choice and 8 regular questions. And to the point of blank files and PowerPoint, Brightspace doesn't do well with big files, so sometimes the viewer doesn't quite show the annotation. If you just download the file and look at it through PowerPoint, the annotation should be there. So once again, the format and length and difficulty is expected to be similar to the sample midterms that are already posted online. The stuff that are covered, it kind of spans about 3 different sections of the course just because of the timing. It does include way back with electrical potential, right? You have to know how electrical potential relate to electric field, how do we integrate to get electric potential at all points in space, etc., etc. Then we have some circuit stuff, capacitor stuff. Then last 2 weeks we looked at magnetic force and creating magnetic field last week using the Biot-Savart law and integration, and then this week using Ampere's law. And then finally, just to take a couple more minutes to kind of go through all the different right-hand rules we have done. A couple of you mentioned your muddiest point that it's really hard to keep track of all the right-hand rules that we've been dealing with. So the first thing to know is that there is not just one right-hand rule. There's a whole variety of right-hand rules, right? It comes up whenever it comes up. The way I kind of organize things is that I use one right-hand rule, the 3-finger one, right, to deal with all my cross products. This is just the one rule for all cross products, right? let me just finish this, and then we can deal with William's question. So with the right-hand rule, you get one vector crossed with another vector would give you the result. So in this case, I would know that this is my thumb, that's my index finger, that's my middle finger. Index finger, middle finger, thumb, index finger, middle finger, so on and so forth. So as long as I have the form for the cross product, I should be able to use this right-hand rule to give me the direction I need. Then I have a whole variety of right-hand rule that relates something that goes in a circle and something that goes in a straight line. So for instance, if I have a torque vector that points out of the page, that means I know that it's going to cause a rotation in the counterclockwise direction, like that. We talked about how for a current carrying loop, if the current swirls with the fingers, your magnetic dipole moment is going to be defined in the direction of your thumb. We talk about if you have a current, a straight current, the magnetic field that gets generated is also given by right-hand rule. And then today we talked about how if you have the integration direction, then we're going to define that direction to be positive current. So hopefully that summarized all the different right-hand rules we've been doing, and that you can apply the right one at the right time. So back to William's question, how do we know which resistant to use for a capacitor problem? So I'm guessing this is referring to finding out the RC time constant. And the resistance is really all the resistance that are in series with that capacitor. So let me open up the midterm then, if we're all good here. I'll stick around for another 5-10 minutes for questions for anyone that wants to. But let's open up that midterm. (2018), eh? (1-4). Oh, let me open up another program so I can write all over this stuff. Okay, let's do that one. So 1-4 has to do with the Hall effect. So what we know is that in a metallic wire current, right, where the current is due to electrons moving from the negative terminal to the positive terminal. So inside here, we expect the electrons to be traveling in that way. And that we're told that this top half has a lower potential than this bottom half. So that means that there's more electrons trapped up on this top here, meaning the force, the magnetic force, is up. So given that my V goes that way, so using my right hand rule, my QV, Q being negative, has to point the other way. In order to have the magnetic field to point upwards, my right hand tells me the magnetic field must be out of the page. So anytime with the Hall effect, right, we're just trying to relate which charge carrier is responsible for the flow. As a result, what is the direction of the magnetic force or field, right, and how that relates to which side gives the higher or lower potential. No further question. We're going to move on to question. How did I figure the force goes up? Good. Well, that's what this is for, right? Compared to the common, which is defined as 0 volts, up here you have a potential less than the bottom, less than 0 volts. So in order to have a low potential on the top, that must mean you have a bunch of negative charges on the top. So that means you have an excess of electrons collected near the top, meaning that your electron has been forced upwards to make that happen. So William was asking about number 3. So this being a problem with multiple sources and multiple paths and resistance and whatnot, we're going to do this basically we're using Kirchhoff's rules, basically, right? So we're given all the resistance, we're given all the voltages, so then it's just a matter of doing your loop rule, your junction rules, and then solving. So was there anything specific you want to ask about that, and what makes that more difficult than otherwise? So don't worry too much about the batteries being exhausted. In this case, all that stuff is, you can think of that as just kind of context. The main thing to actually do the question is down here. So as long as you focus on the fact, so what we mean as a model of a battery being exhausted, all we're saying is that, notice how this is a low resistance, right? These internal resistance are fairly low, whereas these internal resistance are fairly high, right? That's our model of having a battery that is exhausted. It's just the way we model it. But no matter what happens, these sources are still 1.5 volts. Because that's just what the electrochemical reaction gives us. Anything else for anybody? Well, seeing no further question, I guess I'll sign off there. Thank you very much for coming on. Oh, wait. Oh. I make a mistake. Okay, so back to Raphael's question. While the velocity of the electron goes to the right, remember that Q times V goes to the left. And so for the force to be up, the magnetic field has to be coming out of the page. Maybe you're forgetting that little tiny negative sign from the charge. Sorry, that's my bad, Joseph. It should be 4 hours after I hand it out, so that's not 4:30, that's 2:30. So it should be due by 2:30. 4 hours after I emailed it out. Yes, where the sensor is. So thank you once again for paying attention for so long. We will have another live stream next week. And the quiz will be posted on Monday, the midterms on Wednesday, and we keep on going until the end of the term. So see you in a week. Thanks.